Hi, good morning, everybody, and once again, welcome to Pankaj's Echelon Tutorials. In this today's session, we are going to solve one question, that is question number 9, and this is from February March paper 2019. Okay, and this is paper 4.2, right? Now, this particular question, okay, is from electricity. Okay, so let us get started. So question number 9 says that in figure 9.1, this is the figure 9.1, it shows the current potential difference graph for a resistor and a thermistor. So in this graph, you can see there are two graphs shown over here. This is one straight line graph, which is representing the resistor, and this curve is representing a thermistor. Now you may wonder why there is a curve for a thermistor and why there is a straight line for a resistor. The simple answer is this resistor must be an ohmic conductor and this thermistor must be something called non-ohmic conductor, because ohmic conductors obeys Ohm's law, and therefore the graph of current versus voltage is always a straight line for ohmic conductor, and for non-ohmic conductor the graph is a curve because they don't obey the Ohm's law. Well, that was for your information. Now, in this question, sub question A says that calculate the resistance of the thermistor when the potential difference across it is 7 volt. So thermistor is the curve part, okay, the curved graph. Now, if you see here, this is the x-axis which is representing the voltage and y-axis is representing the current. If you see the scale, let me write on the scale also. The scale is it's like one box is represent in the x-axis. Okay, one box is representing, I suppose, 0.2. Okay, and same is true for y-axis also. Okay, one box equal to 0.2. One box equal to, here also you can see this is 2, this is 3, and between 2 and 3 you have 5 boxes. So this is 2, 2.2, 2.4, 2.6, 2.8, and then this is 3. Okay, right? So this is 3. So the on the y-axis also one box is representing zero point 0.2 units. Okay, so this is the scale that I'm writing well in advance, because in future it will be easy for you to take the readings, right? Now calculate the resistance of the thermistor when the potential difference across it is 7 volts. So if you go from here on the x-axis, you come here, this is 7 volt ka potential difference. So on this graph, when you go from this 7 on the top, okay, it reaches over here. Okay, so from here if you go on the y-axis, okay, you will see that it is coming to 4.2, 4.4, and then 4.6, right? This is 4.6. So when the potential difference is 7, okay, your current is 4.6, right? So can I write here, calculate the resistance? Okay, so resistance is equal to V upon I, right? And your V is 7 and your I is 4.6, and your 7 upon 4.6 should work out to, let me check how much it works out to. 7 upon 4.6, 7 divided by 4.6, it works out to 1.52. So let us stick to only one decimal. So we can write the resistance as 1.5. Okay. So this is the answer for A part of the question. Now, the B part of the question says that in table 9.1, tick the boxes that indicate the effect on the resistances of the resistor and the thermistor when the potential difference across them is increased from 0 to 7 volt. So you can see from the graph, when the uh, you know when the potential difference is going from 0 to 7, okay, when the potential difference is increasing from 0 to 7, what is happening to the graph that we have seen here? So in the case of resistor, the graph is a straight line. Okay, now let me tell you here how to actually answer this question. Now here, if you see this graph carefully, okay, on the graph you have on the y-axis you have uh, current, and on the x-axis you have voltage. Okay, so if you want to find out the slope, okay, slope is always y upon y difference upon x difference, isn't it? Y difference upon x difference, right? So y difference means there will be I upon v difference. Okay, I difference upon v, because we have taken I on the y-axis, current on the y-axis. On the x-axis we have taken voltage. So this slope is representing I upon v, right? But you know that resistance is equal to v upon I, isn't it? Resistance is v upon I. So this means that this implies that the slope is nothing but the reciprocal of resistance. The slope is nothing but the reciprocal of resistance. Okay. For this particular graph, the slope is nothing but the reciprocal of resistance, isn't it? So now this is going to help us. Now slope is the reciprocal of resistance. So now here in this, if it is a straight line, the slope is remaining constant, isn't it? So resistance will also remain constant. And as I told you, the straight line is representing for the resistor. Okay, so resistance will remain constant in the case of a resistor. In the case of a thermistor, what is happening? Now thermistor ka graph is this curve, right? So in this curve, what is happening near at this point, near the zero of the x-axis. Okay, the slope is zero. Okay, and slowly the slope goes on increasing, 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 isn't it? So the slope is increasing as you go from 0 to 7. Now slope is increasing, that means the resistance is decreasing, isn't it? Because slope and resistance are inversely proportional. So the answer for this B part, for the thermistor, the resistance will decrease because the slope is increasing. So this has to be the answer for B. Next is C. Question number C says that the thermistor and the resistor are connected in parallel to a 7-volt supply. Calculate the current from the supply. Now, we know what is the resistance of the thermistor and we know what is the resistance of the resistor. Okay, so for the resistance, for the resistor, the resistance is 1.5, isn't it? And for this thermistor also, if you go from here, 7 is the same point. Okay, because both are meeting at the same point. So you can say that the resistance of both the thermistor and the resistor is 1.5 ohms. Okay, so if they are connected in parallel, what it means is 1 upon RT will be equal to 1 upon, now suppose resistor ka resistance is 1.5 and same is the resistance of this thermistor. Okay, so it is 1.5 again. So now if you calculate this, you should get 1.5 plus 1.5, that is 3, divided by 1.5 into 1.5 will be 2.25. Okay, but we want to find out this RT, right? So RT will be equal to 2.25 divided by a 3. This, if you work out, it comes to around 0. Let me check. 2.25 upon 3, right? Okay, so 2.25 divided by a 3 is 0.75. Okay, it's 0.75, right? So this works out to 0.75 ohms. Now this is the total resistance. Now they have asked you the current from the supply. So V equal to IR, and I will be equal to the currents from the supply will be equal to V upon the RT. So V is already given to you. It is 7 volt upon RT is just now we found out 0.75. So 7 upon 0.75, that works out to around 9.2 amperes. Okay, so this is the answer for the C part of the question. C I. Now C double I. the energy transferred from the supply in 5 minutes. Now, energy transferred is given by this formula VIT. Now, in this case, the voltage is given as 7. The I we just now found out, it is 9.2 amperes. And the time is given as 5 minutes, but we have to take the time in seconds. So it will be 5 into 60. If you work out this should work out to around 19 and I think some 350 or so. Let me check it. Okay, so it is 7 5s are 35, right, into 9.2, right, into 60 is 19,320. Okay, 19,320. So this was 19,320. Okay, now this can be nicely written as 19 to 3SF, we can write as 19,000. Okay, and of course it will be joules, right? So energy will be 19,000 joules, or you can say 19 kilojoules, whatever way you want to write the answer, 19,000 joules or 19 kilojoules. So that was this particular question. It was carrying total 8 marks. It was based on electricity from the February March paper 4-2. And that's all for today. See you next time in the next video with some other question. Till then, goodbye. Take care, all of you. If you happen to like my video, please subscribe to my channel. Thank you very much.